Hello, science class. Today I'm just going to give a quick little update lesson and we're going to talk about 1.4, graphing uniform motion, and why we're talking about it. Well, it's going to become very important because we have to use graphs as a tool for us to read and describe motion. So we know position time graphs or distance time graphs, as we will also call them, is when an object travels at a uniform speed and it's going from down below at the 0, 0 mark and going up at an angle, and we need to see the position. However, when we see a graph like this, we have to remember when we're starting off with a graph, where are the positive directions when we look at a full size graph? So remember, up and to the right, positives, negative directions, negative directions. For us, time will always be on this x-axis, okay? So we always have time going along there. So I'm going to put time right here in red. And when we graph it out, hopefully we can do this at home much cleaner than I can, but this is the process we'll go through. That means our positions are going down in the negative way, and we see that right here. And so time will always go on, so we'll have time going in this direction. Can't have negative time, can't go back in time. But as we see there, time will go on, and as we graph it, the position will go down, and as we scale it, at 0, 0, we start here, and then as we go down, there's negative 10 will be right here, negative 20 will be there, and as we can see, we're going down in this negative way. This negative would simply tell us that we're going in the down position or south position, right? So it's not that we can actually go backwards or we're thinking that way. How do you have negative 10 meters? Well, it's our direction, right? So, and we see this graph and it should fit a nice straight line in a uniform way. So it is helpful to actually practice graphing because with proper graphing skills, we should have no trouble identifying the types of motion shown in the graph. And we're going to look at different graphs and we're going to see what kind of motion is actually being displayed. And then we can figure out what does the slope tell us. So if we remember, it's rise over run, so it's that y over x. And so if we took two y points, y2 minus y1 divided by x2 minus x1, we essentially have our distance or our position divided by our time. And what do we know from distance divided by time? Perfect. Hopefully we all thought speed and velocity as well. Here we can see another graph laid out, much straighter line than I drew before, but practice taking the slope and figuring out the rise over run right now. So pause it, and hopefully you get an answer of 14 centimeters per second. This now will lead us into another extension of having a velocity time graph, and it's going to become very important when we need to read what is on the y-axis, whether it's a position, a distance, as we will see like we just did, or is it a velocity, because those two things will tell us something different. And so take a chance now, practice drawing this out as well. Can you identify the type of motion shown in the graph? What was the slope? Can you figure out the slope? What does it tell us? What does it represent? And then determine the displacement of the object. Can you actually work backwards and now solve for d with your velocity and time? So I didn't draw out a bad example, but rather here is another practice one. So if you drew out the last one, it would have been going pretty straight along that line just at the 5 centimeter mark per second, but it would have looked something very similar to this. Now you can't really take the rise over the run because it's not rising. There is no change, meaning the velocity is not changing. But what we can do is take the area under the graph now, and when we take the area, we are actually able to figure out the displacement. And so here we're going 14 centimeters per second, like we just did, and we're going for, I would guess, about 7 seconds. So if we are going 14 centimeters per second, times by 7 seconds, what do we get? We get 98 centimeters. So remember, we're right here, 14 centimeters per second. We're right here at that 7-second mark. Take the area, and the area will give us 98 centimeters. Or if we use our formulas to manipulate, we know it's velocity times time. We get our displacement. So please make sure you have your workbooks out. Please make sure you have your textbook because it does have helpful examples if this is going too quick. This whole unit relies on practicing questions. So please make sure to pause lots, practice frequently.